this is why the field inside of a charged conductor is 0. So I'm going to recap what we did yesterday, just conceptually, and then we'll move on. So yesterday I asked the question, if you had a sphere that was hollow. You guys know the Van de Graaff is hollow? So it's hollow on the inside. You guys know how it works? All right, so it's got a rubber band inside of it. And as the rubber band runs, it picks up electrons onto the rubber. This rubber band has a little scraper on it, a little metal scraper, and it takes those electrons off of the ball, or sorry, off of the rubber band and puts them onto the metal. Now, let's assume that this thing is coated in a bunch of extra electrons. If you were to draw the shape of, no, actually, let's do this different. If you were to take this ball, which is coated with electrons, and take a Gaussian surface on the inside, how much charge it would be enclosed by this Gaussian surface on the inside?
0.
0, right? Because presumably all the extra electrons would be on the outside of the ball. So what would the flux be through this Gaussian surface on the inside? It could be 0. Okay, fine. So let's draw that notability. So I'm gonna, in black, I'm gonna draw a circle. All right, so there is the sphere. Then in green, I'm gonna pick a region inside of my steel ball. Try to center that. It's nice and uniform. And that green circle represents my Gaussian surface on the inside. All right, so let's say I'll use red for electrons. I had a bunch of electrons on the outside surface of that black steel ball. Would they create an electric field? And the answer is yeah, of course they would, right? Which way would the electric field point? Well, toward the electrons, right?
Yeah.
Get it out of space up here. Does that make sense? All right, cool. So we know outside of the sphere, the electric field is going to point inward towards the sphere. Now, here's the thing. Can you prove that the electric field inside is 0? Well, yeah, you can, and here's how. We know, because there's no charge enclosed by this Gaussian sphere, that the flux through this green region is 0. Agree? We also know that because this Gaussian green sphere is concentric with the entire thing, that if there is a field, it has to be symmetrical. Right? And if it's symmetrical, every spot along this surface has to have exactly the same field. Wouldn't you agree with that? So, if the flux is 0, and the electric field all along the surface is the same electric field, what does that mean the electric field has to be all along the surface?
0.
0 by symmetry. Does that make sense? So that means at any point I put my finger along this sphere, what's the field going to be?
0.
So what about right here?
0.
0. What if I picked a slightly larger Gaussian surface and asked you what the field was right here? It'd be 0. What about over here? 0. What about a slightly smaller surface right here? What would the field be? 0. What if you made a Gaussian surface of size 0? What's the field? 0. That means everywhere in this entire region, the field is 0. Wouldn't you agree? That kind of makes sense, right? And then I went on yesterday and said, hey, that's great. That's if you have a perfectly spherical, hollow piece of metal and you charge it up. The field inside is 0, right? It was the same argument as falling through the planet, except now I have Gauss's law to talk about it with. But I said, what if you grabbed a bowling ball and this was a solid gold bowling ball, and you did the same thing to it, and you put some charge on the golden bowling ball, where would the charges go? To the outside, right? So how much charge would be inside of that little hole where my finger is? 0, right? And you say, hey, wait, the solid gold bowling ball is the exact same situation, and anywhere on the inside of this gold bowling ball, the field is 0 because there's no charges in there. You're never encloses any charge. And everybody kind of nods their head up and down and says, yeah, that makes sense, right? But there are a few people in this room who questioned that and said, wait a second. Wait, why is it that the charges move to the outside to begin with?
To repel each other.
Because they repel each other. Doesn't that make sense? They're all negative. They hate each other. They're going to move away. Right? You take 100 negative people, put them in this room, and say, get as far away from each other as you possibly can. Where are you going to go? Presumably to the outside. But what if somebody's, what if somebody's very smart and they say, hey, all you people are on the outside. I'm going to go to the middle where there isn't anyone. Doesn't that kind of make sense? Doesn't it kind of make sense that if you had a solid gold ball and you put electrons on it, some of the electrons would go to the inside? Because doesn't that make sense?
Yeah.
Well, actually, the answer is, I don't know. What do you guys think? Who here thinks that no, all the electrons ought to go to the outside?
Well,
Okay.
you told us to think that.
All right.
Okay, shit.
Who here says no? It makes sense that there ought to be some electrons in the inside. What's the right answer? Both. Or rather, it
Nine.
depends. If somebody tells you, no, there aren't ever electrons on the inside of a piece of metal, guess what? They are wrong. Because, and I'll prove why in a second.
Metal is just the electrons, right?
What if I had something like this Van de Graaff generator? And I started this Van de Graaff generator, and it started depositing electrons on the bottom surface here. And then we all kind of agree, eventually it's evenly coated. But how did they get there in the first place? How did they get to the edge of the metal? How did they get up here? What's the answer?
By being repelled by
Did
each
they
other.
suddenly go, poof, I'm there? No, they didn't do that. What did they do? They moved from here to there. How did they do that?
They moved.
Didn't they have to move through the metal?
Yeah.
So wasn't there a period of time when there were electrons moving through the metal?
Yeah.
Yes. That makes sense, doesn't it? So what if this were a golden, solid gold ball, and I put some electrons down here? Do they have to move up here and then spread out? So it actually takes, think, if you had 1 billion electrons that all had to move through the metal, how long that would take for them to all go from one side of the metal till the point when they're all evenly distributed. How long would that take? A really long time, right? It'd take like forever. It's like 1 billionth of a second. right?
What?
It takes a really long time to get all the way to the other side and evenly distributed. Now, here's the thing. There is that time period. It's called a transient. There's a time period from when you first put the electrons on the metal to the point where they're going to end up, that they were traveling. And during that time period, why were they moving through the metal? Why? You guys know electrons can move through metal, right?
Yeah.
Why would they?
For what?
Why would they migrate in a direction?
The repellent and attract.
Yeah,
Yeah.
because isn't it because there's an electric field causing them to move?
Yeah.
Ah ha ha! So the electric field inside of the conductor is not necessarily zero. Because didn't they have to move in the first place in order to get where they were going? And how do you cause an electron to move through metal? With an electrical field. So there has to be an electric field in the first place to cause the electrons to move to the other side. Now, I'm going to draw a picture. I'm going to draw a better picture than this. A more interesting picture. So this picture is going to be more circles. I'm going to, I don't know, maybe draw a circle like that. And maybe a circle like that. And just to make things more interesting, I'm going to move it off center. And I'm going to say, I'm going to decorate this in gray to indicate that it's kind of, this is all like solid metal. But it's got this lopsided off-center hole in the middle. Check this out. So I've got, I don't know why that happened on my iPad. Hopefully that goes away. So I've got this solid region of metal with a hole. Let's pretend like this is like, I don't know, what's big and metal and hollow? Some sort of tank. But it's got like a thin wall at the top and like a thick wall at the bottom. And inside of this, I'm gonna put a red balloon because I like red balloons. And of course, this balloon is negatively charged because you rubbed it on your head. Yep, turbine. Okay. So around this balloon, isn't there an electric field? Yeah, what direction does it point? Toward the balloon. Okay, so I've got an electric field kind of in this region pointing toward the balloon, right? Over here, it points toward the balloon. An electric field right here pointing toward the balloon, and down here pointing toward the balloon. Agreed? And everybody's okay with that. That all makes sense. Now, doesn't that mean that there ought to be an electric field right here pointing toward the balloon?
Yes.
Yeah? Question mark. So shouldn't there be, like right here, inside of this piece of metal, question mark, an electric field? Yes? Yeah, that makes sense, doesn't it?
Yeah.
There's an electric field right here. It points inward, right? Wait, but, uh-oh. Didn't I say the electric field? Inside, wait, oh no, now I'm confused. Inside of metal, what's the electric field supposed to be? Zero. But it's not zero, is it?
Maybe when you add them all up together.
Say that again?
When you add them all up together, it becomes.
Add what up together? What's there to add? There's a balloon. Right? And metal.
Isn't this like a completely different case though? Is that what
I just put this balloon in here. And now, I agree, there is an electric field in that piece of metal. Now guess what happens to metal if you create an electric field inside of it? What's metal made of?
Electrons.
Atoms, which contain electrons, right? And in metal, aren't those electrons free to move?
They're in C.
So, if the field right here is pointing to the left, what direction do the electrons get pushed?
Right.
To the right.
Whoa.
Do you understand? The electrons get pushed over here to the right side. Now, if they start getting pushed to the right side, what does that leave the left side of the metal, where the electron came from? It leaves it positive, right? So electrons now start migrating to the right and start building up on this outside surface of the metal. Now, there's an interesting thing that starts happening as those electrons migrate. As they migrate, doesn't that start creating a field back the other direction?
Yeah.
Because positive to negative starts to create a field that way?
Yeah.
What does that do to the original field?
Yeah.
Starts canceling it out. And so electrons will keep on moving as long as there's a field present, right? But as they build up more and more on this side, as they build up more and more on this file, the field gets weaker and weaker and weaker. And what eventually happens?
There is no field.
There are so many electrons piled up over here that the field right here becomes zero. But in order to get to that situation, you had to have a lot of electrons migrate. Does that make sense? In the end, once everything is done and there's no field left, what's the field in the metal? Zero. And we know that because there's no more electrons moving. We say the electrons are now in static equilibrium. Do you remember what that word means from first semester? What's static equilibrium mean?
Forces cancel.
There's no net force on the electrons because there's no more electric field. And therefore the electrons don't move. And therefore they're done. And if you think about the number of electrons that have to move in order for this whole thing to be canceled out, it's a huge number of electrons. It takes a really, really long time for this state of static equilibrium to be reached. We're talking billionths of a second. All right? It is not instantaneous. From the time you first put the balloon there to the time when the electrons have gone and done their thing, takes a long period of time.
A long period or a measurable period?
Right. Got it?
Yeah.
I want you to think about it as a long period of time. It's actually like a billionth of a second.
Mm-hmm.
It's actually so fast that it's done. And when we do problems, we just say, oh, the field on the inside is zero. That's only true if it's already reached static equilibrium, but it happens so quickly. All right? How are you guys feeling on this? Do you understand that field building up in the reverse period? Give me thumbs up, thumbs down, or halfway. Okay, so yeah. I've got a simulation to show you that hopefully really, really clarifies the situation. So this is on SimBucket. This is this simulation comes about as a result of a nerd fight I had online with a professor who was looking at one of my simulations and said, "You're explaining this wrong." True story. And I said, "Fine. How should I explain it?" And he said, "Well, you gotta do it this way. You gotta talk about the transient that happens." Like, okay, fine. I'll talk about the transient that happens. So what we have here, this is something called the Drude Model of conduction. Drude Model, D-R-U-D-E. It's a model of a conceptual way of thinking about electrons in metal, where electrons are just ricocheting off of the metal. All right, sorry, ricocheting off of the atom force, right? Which is not a bad model. All right, so why are they moving all the time?
They repel each other and then attraction to them.
It's actually called temperature, right? Temperature means lots of random jiggling, right? So high temperature, low temperature means less jiggling. Okay, we're gonna go back to high temperature. I am going to add electrons to the right side. Check this out. Boom. I'm gonna add some more electrons just for effect. Boom. I'll add some more. What way is the field lines pointing? To the right. How come it's pointing to the right?
More negative charge.
Yeah, because the right side is more negative than the left side, right? Okay, but why are these blue field lines, why are they getting smaller and smaller?
Because more and more are migrating to the left.
Yeah, you see what's happening for the numbers? They're evening out. So what happens when they get completely even?
They disappear.
No, then nothing disappears. It's just that the field is basically zero at this point because the left side and the right side are balanced. Sound good? All right, so when you put electrons on one side of a piece of metal, there is a field as a result of them being there that drives them to the other side. And as they accumulate on the other side, the field goes away. It's kind of an exponential decay situation. Does that make sense? All right, so cool.
Would the exponential decay you ever reach like perfect, like?
Well, there's a lot of jiggling happening. So what do you mean by perfect?
Would like you ever reach like all these electrons on the center? Nothing.
Well, let's see. 188, 191, 90, 196. Kind of jumping around back and forth.
Yeah.
Every once in a while, an arrow will pop up this way, but that'll force them back over that side. There's a little bit of an inertia going on in this model,
Okay.
which is way more inertia than actually exists, I think. You can, I believe, have some inertia in things like antennas, where but it's effectively inertialess for our intents and purposes. Right? The electron has so little mass that it's got pretty much zero inertia. All right, we good? All right, so this explains why if you create a field, electrons in a conductor will shift over to the other side to zero out that field. And one of the things that's not modeled in here that I kind of wish I did was like, hey, let's apply an external electric field. And that would force all the electrons over to this side, right? Until that field was canceled out. Does that make sense? It actually wouldn't force all the electrons over. It would just force enough over such that the net field on the inside was zero. Does that make sense? So, we say for a conductor in electrostatic equilibrium, it's already reached the point where the charges have built up on the edges such that the field on the inside is zero. I'm going to go ahead and draw that now. Here's what that would look like. We know that that will cause, once the charges have built up, that will cause this to be zero here. And here, no field anywhere inside of this metal. It's not some magical thing. It's a result of billions and trillions of electrons moving in whatever direction they need to go, however they need to move, to achieve that state. And you asked, the original question was, are there electrons in the middle? Sure. But is there a net charge in the middle? No, because if there were, that would create a field that would push things around. And we know as long as things aren't moving anymore, then there must be no field.
Okay.
If they are moving, what do we call it? Starts with a C. Current. All right, which does exist temporarily. Actually, somebody raised the question, hey, how do you make an electric current that keeps moving after that first billionth of a second? Do you guys know the answer to that? Like, back to the Drude model thing, they're like, how do I make this electric current just keep on going? What's the answer?
Keep betting on it.
Yeah, add some. Oh, we're starting to get weak. Add some more. Uh-oh, starting to get weak again. Add some more. Starting to get weak again. Add some more. Do we have any devices that are designed to just add charges to one side of a piece of metal? It's called a battery. Oh, by the way, it'd also help if you started sucking some of the charges off the other side too. Otherwise, the thing just gets crazy charged. All right? Add some to one side, take some from the other. Just keep on doing that. And as long as you got energy in your battery to keep that happening, the charge keeps moving and the current keeps flowing. That's what current is. We good? All right, cool. So actually, it's an interesting question. We teach electrostatics first. But to me, like, you can't really understand what's going on in electrostatics problems unless you understand how charges move and why. Isn't that interesting? Like this whole Gauss's law, electric field inside of a charged conductor is zero thing, you gotta know about current to know that. Got it? All right, cool. So, not that one. So the final state, after all the charges are moved and there's no field anywhere, you end up with positive charges on the inside and negative charges on the outside. Good? And oh, by the way, is there a field outside of the conductor? Like around the edge? Yeah, what way does it point? Inward. Does that make sense? All right, now for the bonus round. If I were to draw in green a Gaussian sphere like this, and this is my Gaussian sphere. What's the charge enclosed? How much? Give me a number.
0.
0. How is that possible? Am I saying there's no charges inside of this sphere?
No, but there's positive and negative cancel.
Positive and negative in equal quantity, so the net is 0. And that's actually how you do problems. You say, well, gee, if this balloon has a charge of negative Q, how much Q has to be deposited on the inside of that metal? Positive Q. Does that make sense? All right. Because I know the field here is 0. All right. Is everybody good?
Yeah.
So the flux, the charge enclosed in this Gaussian surface is 0. Now, of course, we could do a Gaussian surface around the whole thing, like this. How much charging is enclosed by that? Is it still 0?
No, it's
No, now it's negative. Do you see it? All right, because you got negative Q, you got positive Q, and then you've got negative Q along the outside edge now. Does that make sense? Oh, what if you went to Gaussian surface just around the balloon? Is that 0? No, it's still negative Q. Do you guys got this?
Yeah.
All right, I think I'm going to stop here. This is the foundation for all the shell problems that we're about to do, is you have to understand why inside of a conductor, in the meat of the metal part, there is no field. And that's not something that's just magic. It happens over time. The amount of time it takes is on the order of a few billionths of a second, but it's not instantaneous. Do you understand?
Yeah.
Is everybody good? All right, cool.